Hello everyone, good afternoon and welcome to all of you, distinguished delegates, presenters and participants from SARC member states and region around the world. On behalf of Director SARC Energy Center, I am thankful to all of you for joining us in this capacity building event, online training of stakeholders on digitizing industrial motor system for energy efficiency. I am Tularam Paudel, Research Fellow in Energy Trade at SARC Energy Center, Islamabad. I shall be moderating for all 5 day sessions. Ladies and gentlemen, this 5 day exclusive training is organized by SARC Energy Center, and we have invited the resource person from various countries: China, India, USA, Switzerland, Finland, Germany, and Hungary. I am also grateful to Mr. Hubo from Top 10 China for taking the lead in this training. Now, without any further delay, I would like to invite Dr. Tanvir Ahmad, Deputy Director, SARC Energy Center, for the opening remarks. Over to you, sir.
Thank you, Tula. Dear participants, presenters, trainers, ladies and gentlemen, I welcome you all to this training, online training on digitizing motor system for energy efficiency. Digitization, of course, is a very important topic these days, and when it comes to motor industry or overall the industrial system, we know that it is a very energy consuming area in overall the world. But in SAARC region, this region is now a developing region. More and more industries are coming, so we need such things where which without any cost enhancement we can reduce the energy consumption. This is the basic purpose of this training, and I'm very delighted that we have a very diverse group of trainers here. Thanks to Tularam and the trainers. Ladies and gentlemen, in this training we have invited trainers from 8 different countries, where the lead is the Top 10 China, led by Mr. Hubo. So special thanks to Mr. Hubo for being here with us. That's it from me in the end. Once again, thank you all for joining this training event. Tula made a lot of efforts in making this training a success. I'm hopeful that you will learn a lot during the 5 days. With these words, I declare this training session open and wish you all a very comfortable learning and knowledge sharing experience. Over to you, Tula. Thank you.
Thank you, sir, for your valuable insight on the subject and wishes for comfortable learning and capacity building session. Ladies and gentlemen, now on behalf of resource person, I would like to invite Mr. Hugo from Top 10 China to give the overview of the training. And Hugo started his career by working for China Standard Certification Center in the field of energy efficient product certification, standardization, labeling, and now he is technical manager in Top 10 China. He has conducted many studies on energy efficient products used in household, office, and in vehicles. He introduced Top 10 motor from Switzerland to China and has been working and providing training on form demonstrator, which is software developed by Swiss Top Motor, and his area of interest cover testing, standardization, and market research. Over to you, Mr. Hugo.
Can you see my screen now?
Yeah.
Okay, so maybe I can start. So, and everyone, maybe good afternoon Chinatown, and also maybe good afternoon in Pakistan, but morning for the Swiss time. And I'm happy to see that I can have 2 Swiss colleagues to join us, and also it's my honor to meet the director from the SAS Energy Center. So I'm Hubo. I'm the the organizer, coordinator, and also the trainer of this interesting training program for this organization. So right now I'm going to introduce to everyone that the overview of the training program, because I'm responsible to to identify the trainers and also to design the topics. So I think it's good for me to give you a big picture what I'm going to see. But I think the first I want to highlight that, that's the slogan, what top 10. And also I worked with Conrad for the last 10 years. See, I think that's a slogan I want everyone to, think about it. That is energy efficiency is the first source of energy. Previously energy efficiency considered could be something different, but I think right now we consider energy efficiency is the first source of energy, especially in the EU and also in China, the policy context. Energy efficiency has been put high prioritized in policy context. I know that there are some officers from the South Asian countries to join us. I hope that this can be also, can be good in your future work. Second is why motor, because motor system consumes huge electricity. This is research from the U4E, from UNEP's U4E program. The motor system consumes more than half, 53% of the global electricity. I think this graph will be shown again and again by other speakers, by other trainers. They will show you how important of the motor system because it consumes so big share of the global electricity and also energy. Second is, this is the graph actually from Conrad. I cited at the very beginning. I found that from his presentation, he does not show this graph, but I think the most important is motor system efficiency is the key. Based on this concept, because I don't know the background of the trainees from this South Asian region, so based on this concept, I designed the topics or subjects for 5 days. First day is for the system approach. Second is the digital pump demonstration and training. I know that everyone has already get the schedule on your table, but I want to explain to you what's something behind, because when we design this training schedule. The second is the pump demonstrator. I'm involved in this development process. I want to show you the front of the demonstrator, but also something behind this. The third is for the VFD control and also digitalization from I think from the University of Bern. And they have Vitili, the IEC TC member from Switzerland, is quite experienced, expert in this field. And the fourth day is my solo day, it's my day. So I will give you some inception of the in-depth insight of the digitalization of motor and also even other IoT system and also some industrial communication protocol like Modbus, and also the next day could be the OPC UA. I think the final day could be digital communication protocols with ABB expert, because ABB invented very creative, their solution called the ABB ability, something very creative solution. I think that we can learn from it. I think that's the trainer's profile. I think Tula and also the director already mentioned that we have a bunch of trainers from different backgrounds. We have diversified institutes we have experts from universities, from the companies like ABB, and also from NGOs like CLAS, and also with research institute like China National Institute of Standardization, and also like top 10 actually is an NGO or technical consulting service company. I think we invited a bunch of trainers from all backgrounds. I want to highlight that Conrad and also Andrea, they work and also are working for IEC, the TC committee. I think that they are the front runner in this field for motor efficiency and also international standardization. And also there may be seen is China National Institute of Standardization. They are quite pioneering in this kind of process. Of course, we have the speakers from from a lot of countries. I don't want to repeat again, but actually we have the speakers from from China, from different time zones, from morning to afternoon or even some evenings. I think that's a combination. I think that's my perspective of the training. Finally, I see that we just only present something. We want to share you with presentations, with speech, with blah blah talk, and also the slides. But also we want to practice. That's why we prepared this kind of free open source. That's free. Maybe for the first year, a free open source for you to practice. I think Rolf later will present you Sotia, Eli Plus, and also motor system tool, which are available and also free for you to experience. You can download it and you can experience, you can practice, and along with Rolf's, the presentation, and later the presentation will be shared with you. You can practice by your own. I think that's difference from our training with others. And also we have Mapsy, and also it has online pump demonstrator. The last one, Modbus tool, is not free, but I think it's quite good tool for you to learn the industrial protocol. I think that's all my introduction, and I'm happy to see you again. So you can send me mail or contact me anytime that you want, and I will give this floor to Tula again. That's right. Yep.
Okay. Thank you, Ubo, for providing the brief introduction as well as this schedule and how you arrange this training from the point of the resource person as well as from material. Dear participant, we have uploaded the material in our website, reference material. You can browse it from the www.sarkenergy.org. We have uploaded there the 3 reference material as well as 7 link for the tools and software. So moving forward to technical session, the theme of today's session is inauguration and efficient motor system approach. Today we have 2 technical slots that will be covered by 2 eminent speakers, Mr. Konrad U. Berner from Switzerland and Mr. Rob Taiwan, Impact Energy, Germany. Dear participant, you can send the question by typing your question in the chat box of go to webinar window at any time. So we'll try to address that during presentation or at the end of each presentation. Now I would like to invite Mr. Konrad U. Berner to present on overview of motor system energy efficiency improvement. To give brief intro, Mr. Konrad got his diploma at the ETH in Zurich in 1966 and completed a master degree at University of Pennsylvania, USA. He has been working since 1974 in energy efficiency sector. He was involved in launching the Swiss Agency for Efficient Use of Energy, SAFE. Since 2004, he has been engaged in energy efficiency project, research and policy work in industry. He has been an expert for the development of eco-design, regulation of motor, pump and fan. In 2014, he founded the international consultancy Impact Energy in Zurich and he is the president of the board and he is active in IEC TC2 motor and SC20. So he has lots of experience, very vast experience, maybe more than 35 years. So I think we will be learning more and more from him. So over to you, Mr. Konrad, please. You may go into the presentation.
Thank you, Tula Ram. Thank you, everybody, for joining us. Good afternoon. Can you see my screen?
Yes, no problem.
You can
Okay.
make it bigger.
I make it bigger.
Please.
Here we are.
Slide.
Okay. I'm delighted to meet all of you. I must say I have been in this region where our audience is coming from, the SAARC, but I don't know all the countries. And I'm very happy that we are able to give you some information from our experience. We might want to visit all your countries and get a personal contact for the training. But this time, you know why, in the age of COVID, we do everything on the computer. My topic is the introduction to the 5 days training. It's under the title of Digitizing Industrial Motor Systems for Energy Efficiency. And you can see on my introductory slide there a motor and pump installation is being mounted on the top of a big purification plant. Now, I chose the title Efficient Electric Motor Systems, Overview of Motor System Energy Efficiency Improvement. And as I said, my name is Konrad Brunner. I'm an energy efficiency advisor since many years. Therefore, I have many gray hair, and I'm based in Zurich, Switzerland. This is for you to understand the use of electricity worldwide, global electricity end use. In the graph, you can see on the left side a part which is greenish, which is the consumption in buildings, electrical energy consumption in buildings. On the right side, you can see a part which is bluish, electricity consumption in industry. And below, you can see a smaller part in red, transport energy use, and agriculture, a little bit bigger electricity use. The big use is in buildings, in appliances for cooling, and in industry for pumps, fans, and compressors, and for process heat. When you look at electric motor systems, you can see within the dotted red square, this covers the part of the buildings which is appliances in cooling. Every refrigerator, every air conditioner has a compressor, and the compressor is driven by an electric motor. It covers a large part of industry with the pumps and the fans, the compressors for air and the compressors for cooling, and mechanical transport movement in industry. And it covers a large part of electricity use in transport and a part of the electricity used in agriculture. Now, the red dotted square is according to research done by the International Energy Agency, is 53% of the global electricity use in the year 2016. I don't think that this number has changed. This number can be different in different countries. It will be higher in very industrialized countries. I think the number in China is up to 56%, and it is lower in countries which have a larger share of services. Then it might go down to 45%. I think each of your SAARC countries have around 50 or 53% of electricity used for motor-driven system. This means, of course, motors are the big chunk of electricity to be used, and motors are the big topic once energy efficiency is the main topic. This doesn't mean that we shouldn't talk about lighting. This doesn't mean that we shouldn't talk about electrochemical and process heat, but for today, I think we have chosen the big chunk, the motor-driven system, as the topic. Electric motor systems are used in many applications. Electric motors drive pumps and fans and air compressors and cooling compressors, transport systems, handling and process systems, and many other things. On the right side, the pie, you can see we call them the big three: the pump, the fan, and the compressor. Together, they use something like 3/4 of this global electricity used in motors. The compressors, the 34%, are split between the part which is used for cooling compressors and the part which is used for compressed air. The fan, the 24%, means it is used for all kinds of ventilation and blowers. The pump, the 17%, covers the circulators, small size, glandless, until the big dry running pumps of all kinds. Therefore, these three elements are the key of electric motor systems. I've said already that 53% of global electricity is used for the motors, and the last number is important. I think Rolf Thieben will then go into more detail. When you just look at industry share is about 60, 70 or more % for electricity used for motor-driven systems. Now I want to, as an introduction, quickly explain what we understand with the term a motor system. And I have show you a graph where from the left side you have the power supply, and then you go all the way through all the elements. On the right side you have the process components, the mechanical controls. That means the air pushed through the ventilation system, the water pushed through the pump, the pipes, and so on. There are 5 key elements. The first one is the power equipment. That means between the supply from the high voltage, you have to have a transformer and switchgear. Then you have the controls at the entry of the motor. In the easiest way, you have a starter, or you have something like a variable speed drive, an electronic system that you're able to control the motor speed. Then you have the electric motor by itself. Here it is sample. Then you go in the 4th box to the mechanical elements like coupling, transmission, also gear, all kinds of belts or chain, if you have a clutch or you have a brake. And then you come to the key element, the application of the driven equipment, the production machine. This can be a conveyor, a pump, a fan, or compressor. And then you have already something like a flow of air or water, of a motion of machine. And then you come to the process components and the mechanical controls, which are the pipes, the throttles, which you want to avoid in the future, the valves and the dampers. Now, I want to explain you something which is very important for the global improvement of electric-driven motor systems. I put a blue box on the left side. The left side includes the power supply, the power equipment, the controls, and the electric motor. All these elements are standardized by the International Electrical Commission, IEC. They make the standards for testing, for efficiency classification, for all things electrical. And then to the right side, the coupling, the driven equipment, the process components, they are mechanical components, and they are defined, their standards for testing and for efficiency are defined by the ISO, the International Standard Organization. These are 2 completely different standardization systems, and I'm here to say I deplore that for the last 30 years, the blue group and the red group did not really communicate together. And now I can tell you, if you need to have an energy efficient electric driven motor systems, the blue side and the red side have to communicate. I'm happy to announce that since this year, there is a group which is called a joint advisory group that starts to interact and starts to come up with standardization that go from the power supply to the actual use. This we call wire to air or wire to water for the kinds involved. Therefore, from this year and hopefully stronger in the future, there will be a cooperation between IEC and ISO on electric motor-driven systems. Now, let's quickly look at electric motors. I show you a graph where on the horizontal axis is the output power in kilowatt. It's a logarithmic scale. It's based on an IEC standard that defines the efficiency classes of motors. It was published in 2014. It goes from 0.1 kilowatt to 1 kilowatt, 10 kilowatt, 100 kilowatt, and 1000 kilowatt. And as I said, it's a logarithmic scale. This standard is available at www.iec.ch. The standardization organization IEC is seated in Switzerland, therefore the ending is CH. On the vertical axis, you have the efficiency of these systems. I didn't draw it from 0 to 100, but I drew it from 50 to 100. And then you have 4 different lines. Before I go into the details of the 4 lines, I want to remark that you see all the curve start on lower efficiency for small machines and go to much higher efficiency on the right side. Therefore, a bigger machine is always more efficient. You can also see that the differences in efficiencies from these four efficiency classes, the differences in the efficiency from these four different classes is very large on the small side and few percentage only on the high side. I want to explain them to you. The red line on the bottom is the IE1 standard efficiency. These data are all based on a 50 Hertz supply, which I think is also very typical for the SAARC region. The yellow one is the IE2, the high efficiency motor. That was the standard until about the year 2000. And then the green one is today's standard for a premium efficiency motor. It's called IE3, premium efficiency. You should keep that in mind. And then the blue is sort of the REACH standard, which starts to come into the market in Europe and in the US, and maybe slowly also in the Asian region. This is called IE4, super premium efficiency. What the curve shows that on the lower end, in the 0.1 kilowatt area, the difference of efficiency of the four classes is from 50% to 70%. That means a 20% gain in efficiency. And then on the right side, you can see from the IE1 to the IE4, you have something like a 3 or 4% difference from the motors. Therefore, the question is this business only important for the small machines? Is it not worth to go into more qualified, more quality products because the difference is so small? I want to make an easy calculation with you. If you start at the lower end at 0.1 and you improve 20%, this means 20% of this is 100 watt. The improvement will be 20 watt. When you go from here to here, your efficiency is 20 watt. When you go at the upper end and you go from here to here and you save, say, 4% from 1,000, then you save 40 kilowatt. 20 watt on the left side, 40 kilowatt on the right side. That means to be very highly energy efficient with big motors brings a lot of savings, a lot of kilowatt reduction, even if the difference in percentage is very small. Think about that and think what that means for your applications. Now, one of the key elements we found for motors is minimum requirements for motor efficiency. It took a long time to make this system popular. It started in the US some 20 years ago. It came to Europe and it's now spreading also to Asia. There are different elements to make minimum requirements for motors. First of all, you see again these four different levels, IE1, IE2, IE3, and IE4. Then the second column here is the testing standard. It is imperative that when you make performance standards on the last column, minimum requirements, you need to have the same testing method for the motors. This was not the case before this standard IEC 60034-2-1 was published in 2014. Before that, that means before 7 years, it was not clear whether the method used in the US or the method used in Asia, the method used in Europe would render the same motor tested with the same results. Now we have a unified method. Now we can say safely the motor tested according to this IEC standard has a reliable result. Within this standard, there are many different kinds of testing method, and we generally refer to what we call preferred method that is suitable for all general application, and it is the summation of losses with a load test. And the additional losses are determined from residual loss. And now on the right side, you have the countries that have already by legal decisions of the national policy requirement, minimum requirements for motor efficiency. And you can see, I'm sorry, I'm always jumping a little bit. You can see that at the highest level, the European Union and the UK, for a small fraction of the motors between 75 and 200 kilowatt, have announced from next year, 2022-23, to have IE4 already as a minimum requirement. That's a breakthrough in energy efficiency requirements, and I think this will help other countries to move up there in the next couple of years quickly. And then you see a long list of countries who have adopted IE3, the premium motor, as their minimum performance standard, among them Canada, Mexico, USA, South Korea, the European Union for the smaller sizes, Switzerland, I'm proud of that, Japan, China, Israel, Singapore, Taiwan, Brazil, Ukraine, Egypt, Turkey, and Saudi Arabia. So far, I don't see any of the SAARC countries in this group, sorry to admit. And then in the IE2, the lower level of efficiency, it's called high efficiency, but today we call it lower because this is the premium now. We have Australia, the European Union for the very small motors between 0.12 and 0.75. We have Chile, China, Peru, Colombia, New Zealand, Israel, the Arab Emirates, India, and Ecuador. That means only India, if I'm not wrong, in this whole list is in the minimum requirements for motor system and only at the IE2 level. And if I'm correctly informed, you can tell me if I'm not up to date on that. I would appreciate this information. All the others have not yet minimum performance standards for electric motors. I want to emphasize minimum requirements for motors sold are imperative. If there is no mandatory standards for the minimum requirement, usually the buyer buys the cheapest motor. We all know, I'm sure you know, that the cheapest motor at the purchase time is not necessarily the cheapest motor over the lifetime of the motor. Many higher efficient motors pay themselves, pay their a little bit additional cost within 1 year or 5 years. And from then on, the higher efficient motor is profitable and you make higher money losses if you have chosen the cheaper motor. And we also noticed in all countries in the world, this was like that in the US, who started the minimum requirements. It was like that in the European Union that followed. Only if there is a mandatory level for minimum requirements, then industry users will buy the more efficient motor. Otherwise, they tend to buy a cheaper motor, which is not a benefit for the future use of electricity. Now, I want to give you 6 points that I feel are key for energy efficiency in motor systems. And this is an overlook, and I'm sure the following presentations by my colleagues, the other trainers, will go into much more detail. But these 6 points are sort of the strategy behind getting efficiency for industrial motor systems. I call them industrial because I mean the minimum of motor size we talk about is 0.1 kilowatt, and it goes up to 1,000 kilowatt. But we are not talking about a very teeny 2-watt ventilator, which I have in my computer. Point 1, design for necessary demand. Necessary demand. That means the pressure and the flow of your ventilation or your pump, the capacity and the temperature you have to reach. All these parameters should really be calculated or measured, and you should design your system only for the necessary demand. This leads to point 2. If you find a machine in operation that is too big, Too big means it will be operated most of its time in partial load at 50% of the possible output power, or even 20% or 10%. If it is run at lower than optimum load of the system, then the efficiency is lowered very much. Therefore, point 2, downsize all components to actual demand. Not only the motor, but also the converter, if you have one, or actually also the pump or the fan. All the components should meet actual demand, which I call necessary demand also, and then they operate most efficiently. Point 3, use your motor only when necessary. This sounds trivial, but we find many industrial applications where machines run 24 hours, 7 days a week, and they are run in summer equally on a fixed load, and they're run in winter equally on a fixed load. This is not necessary. Use motor only when necessary means turn it off when you don't need it at night, turn it off when you don't need it over the weekend, lower its capacity when you need less in winter, and adapt your system to the time you're actually needing the motor. Point 4 is following to point 3. You're not just only turning the motor on or off, but on point 4, load control is imperative for all changing load applications. Load control means to use a variable frequency drive that has the capacity of changing the motor speed, therefore lowering the output of air, of water, or mechanical power, and therefore saving a lot of energy. Don't use load control on every application, but use load control when you have really a changing load application, which means you have industrial production in batches, or you have a summer condition which is different from a winter condition, or you have a night condition which is lower than a day condition. Point 5, go to direct drive wherever possible. Direct drive means avoid having gears and belts between the motor and the actual application. Direct drive saves a lot of space, a lot of energy, a lot of wear, and gives you a much more efficient system. And 6, use digital monitoring and remote control for new application. I will come to that point, and that's part of the title of this training, Digitizing Industrial Motor Systems for Energy Efficiency. I will explain you what it means. Now, the good news, when you do what I say, point 2, downsize, when you use point 4, load control, when you use direct drive, point 5, you save a lot of money in the installation. Your new motor system becomes smaller, more compact, and is actually more efficient. That's what we want. Now I quickly run through all the typical applications. This is a fan, and it has this traditional drive with 2 pulleys and a belt, maybe a V-belt, and it has a motor and has no variable frequency drive or something. Then you have an old-fashioned pump with a motor, and the actual pump here, it looks like this was built in the 20th century, not in the 21st century. Here you have an air compressor with dual compressor stages, with a huge motor with the respective necessary cooling or heat use. And here you have a motor installation for pumping. This I want to show you that you are not blinded when you go to visit industries. We visited this factory some 10 years ago, and we were surprised how nicely the motors and these cages and the pumps were presented. We found they were just freshly painted. Then we looked at their rating plates, and we found that they were produced by BBC, and the company BBC went out of business in 1988. That means these machines are over 30 years old. They should be replaced, downsized, everything I mentioned in the last slide. They look nice, they can be recycled, Their steel can be recycled, their copper can be recycled, their aluminum can be recycled. 98% of their equipment can be recycled, and they can be replaced by smaller and much more efficient systems. Don't be blinded by nicely painted material. This is what a modern motor can look like. This is an example from ABB, a synchronous reluctance motor driving a pump. It's IE5, that's above what I call the super premium motors, and this is sort of the state of the art of new machinery. I also mentioned the variable frequency converter, which will become a standard application for all things where you have a variation of load. This is an example from Danfoss driving with a variable frequency converter. This is from the mains, from the grid, and it goes through the converter, and then it is supplying the motor with a variation of frequency and can therefore change the output of the compressor. Now, let's talk about the new world. Let's talk about everything which is digital. I want to call the digital motor systems, and I want to mention 4 different elements that could be in this framework of digitalization. The first element is condition monitoring. This has been done for a long time, and the goal of condition monitoring is to avoid a system failure. You want to be informed quickly whether your system performs 100%, where it's on or off by a failure, or it shows already conditions that will shortly lead to a failure. The second element is that you have, for every larger motor, remote control over the WWW, and with this you can not only check is it running or not, but you can go to performance check. Performance check means what kind of load is it actually delivering? Is it following the required load? Is it performing the way you want to have it? And you can look at this from a command center in a factory, or if you have a smartphone, you can load the machine here and you can look at it from far away. I think Hubo will later show you things like that, where you can operate the remote control from your handy and you stay at home. The third issue is load control. Here, it's not about whether the machine is working and whether it does what you want, but here you want to optimize energy savings. That means load control is comparing today's performance with yesterday's performance, this week's performance with last week's performance. In this case, you can decide whether the performance is actually living up to what you want to have it. And the fourth point, which is now sort of what you want to do in the future, it's what we call a digital twin. This graph shows you a digital twin. This is your machine, physical, mechanical, electrical, and this is what you have on your computer. Not just a drawing of the system, but a twin in the sense that you know all the parameters of the machine. And if there is something not what you like to have it, I'm sorry, I jump back and forth. If you have something that you don't want to have it, then the machine is actually, it's possible to immediately go at home, define where the problem is, and then jump to the actual machine and do the improvement which is necessary. Yes, I have to go to full screen again. So, next one is, here I'm showing you some types of digital centers for motor monitoring. All the big manufacturers, I show you only the Brazilian from WEG, the Swiss, Swedish from ABB, and the German from Siemens. All of them propagate digital centers for motor monitoring. These are typically small boxes like this one, which is fixed on the outside on the cast iron stator. Here it's a flat box, which is mounted here on the side, and here it's a little oblong box, which is mounted here. All of these sensors can easily record the temperature of the machine, the vibrations, and the sorry, the operating time. That means on or off. maybe I say, because all of the three of them, all the three companies are trying to reach that level, they can also check and record speed and torque of the machine. That means the actual load condition the motor is operating. And they do that by monitoring through the stator the actual electric or magnetic flux that is within the machine. All these sensors have a capacity of storing the measured data and then to relay it through the World Wide Web or through any kind of device, any kind of a system, to a central operating center where the data of performance of each of the machines can be analyzed and motor and used and the situation improved. Now, I want to quickly tell you what I call the number one case. The number one case has to do with the economy of a much more efficient motor systems. The outset is for me any 0.1 kilowatt to 1000 kilowatt nominal output machine. It stretches the whole horizontal axis of this efficiency diagram. And it's not important. It could be a pump, a fan, a compressor, anything that rotates. That's sort of a general appreciation of what happens when you make efficiency. Then the machine at the outset, in 90% of when we go to factories and make factory audits and try to help the owners and the operators to improve their systems, we see oversized machines. Rolf Thieben will show you some results from our analysis. We show a high degree of machines operating with fixed speed. We see a lot of gears and a lot of V-belts. And we see, of course, an assembly of current market components. Now the system improved. I summarize the elements I've already mentioned before. You can, by measuring the performance of the machine, downsize it to the necessary level. You can introduce adjustable speed by using a variable frequency drive. We can go to direct drive by eliminating gears and belts. You can get efficient components, and you can start to use, which is now the new technology in the digitizing age of motor systems, remote control. Now, what does it mean? The efficient motor system means, number one, supply meets demand. Finished with oversizing. Finished with this fear that your motor will eventually not be capable of reaching the nominal required load. Oversizing is an old-fashioned, traditional approach to motor from the time when, one, motors were very much prone to overheating and to catching fire or to burn and to destroy themselves, and at the same time precise calculation methods or measuring methods to really calculate or size a machine appropriately were not available. Today, the motors run much cooler, they don't overheat, they don't burn, and you have all the tools to really define the demand. Second, time of use, run only when needed, not at night, not at weekend if you don't use it. Number three, many of these more advanced systems have standby losses. The standby losses come from motor controls, like from the variable frequency drive, from heating part of the oil and the gear of the motor and the gear. Many other things have standby losses, and especially in smaller machines, there can be a considerable part when you operate only 1,000 hours a year, and you have for 7,600 hours standby. This can be more energy wasted than energy used during operation. Number four, motor connects to pump fan directly. This is certainly an imperative for new systems. When you have an old systems, you have to think about whether you can benefit when you eliminate the gear and eliminate the belts and go to direct drive. It's not possible in all the cases without a large change of the application, but it's possible in many cases. It saves you maintenance, it saves you space, it saves you money, it saves you energy. 5, the load control is necessary, should be a standard variable frequency drive, but it should be only used in applications where actually variation of load is necessary. I know that my colleagues afterwards will tell you that in much more detail. And number 6, use high efficient components in the motors. Today, this is IE4. I would say when we talk SAARC countries, it might be IE3 or IE4. Not in every application you can afford the highest efficiency. Maybe it's not even available right there on time, but IE3, I'm sure premium motors are available all over Asia today. Then use a VFD. They're also classified. They have an IE2 or IE3 class for the variable frequency drive, and choose at least an IE2 if you want to have a successful variation of speed of the motor. And then when you select the pumps and fans, use, we call that BAT, the best available technology. In Europe and in the US, we have already minimum requirements for that. We have rules and methods how to calculate the efficiency of pumps and fans. We have requirements that this should be shown and on the rating plate, but I'm not sure whether in the SAARC countries this information is available. But make sure you get a high performing pump or fan or compressor, not just the cheapest one available. And number 7, as I have shown, try to go to remote control for middle and large size machines in the future. Now I want to touch a final subject, which is not so important in Europe. It is very important in Asia. It's a question of repair an existing system versus buying a new motor. I have tried to summarize all the discussion points for the repaired motor on the left side and the new motor on the right side. A repaired motor goes into repair maybe every 50,000 hours, maybe before. It goes into repair because the bearings are not good anymore, or because you have some problems in the winding, electrical problems, heat problems, insulation problems. What do you do when you repair a motor? First, you have to dismantle the motor. That means you have to take it out of where it actually is installed. You have to dismantle, rewind, and assembly. Maybe for this process, you have to ship it to a qualified lab and a workshop. And this whole thing takes some days or even weeks until you get your motor back, rewound, nicely greased, and back into operation. In all surveys by research, we know that efficiency is usually decreased while the motor is rewound. There are very rare exceptions when you have a very high qualified lab that spends a lot of time in filling in the same amount of copper wires as they had pulled out before, and then the efficiency can be again something like the same, like what it was before. It's never better. It's usually lower when you rewind the motor. Then the third bullet, repair is costly. Repair costs below 10 kilowatt motors usually higher than when you buy a new motor. The problem with rewinding is also you rewind a 10 kilowatt motor and at the end it's still a 10 kilowatt motor. You cannot use what I said before, the elements of downsizing and changing other elements in the motor. You also have the same type of motor. Usually you stay fixed speed after the repair. It's pretty complicated and sometimes dangerous just during the repair to add a variable frequency drive. Many of the old motors are not really capable, or they don't like to be run by a variable frequency drive that can get problems with high voltage, and they will also be damaged. An old motor runs hot, it needs more greasing, and therefore it needs more maintenance. and it will always have the risk of failure again, even after the repair. And to summarize that, a repaired motor is never a new motor. A repaired motor is a repaired motor, period. When you look on the right side for the new motor, you can see, first thing, you have to plan ahead for delivery of new motor. In the repair case, you usually start when the motor breaks down, and then you have to rush to get it rewound. In the new motor alternative, you can say this motor, small motor, is 10 years old, or this larger motor is 20 years old. It has to be replaced. There are better motors. You plan, you define the new motor characteristics, and you order it, and then you can get it, the old out and new in, one-to-one, and you don't have to disrupt your production line. When you buy a new motor, you can increase the efficiency to go to IE3 or IE4. In the repair, you have maybe an IE1, and you keep being an IE1. As I mentioned, in the repair, the cost of the new motor above 10 kilowatt is maybe cheaper than when you do a repair. In the new motor alternative, you can resize it, downsize it. This is easily possible. You can also buy a better motor type. You can maybe go from 4-pole to 2-pole to run it faster for a ventilation system, and you have less heat that you have to deal with. The motor runs cooler. That means less greasing is necessary. Less greasing means less maintenance, no failure, and the use of variable frequency drives is easily possible because every new motor you buy today is capable of dealing with the spikes of voltage you get from the variable frequency. Therefore, we recommend, especially for motors above 10 kilowatt, below 10 kilowatt, to always start with a new motor. And the last line is, when you throw the old motor out and buy a new motor, the old motor can be easily recycled. Everything you have in the motor is recyclable, except maybe the paint. 98% of the motor can be easily recycled. Okay, this has been my presentation. I thank you for your attention, and maybe there are some questions. Thank you very much.
Thank you, Conrad.
Thank you, Mr. Kunal, for a very excellent presentation. So you highlighted many important and basic things regarding motor and efficiency. Some of the point you mentioned that industrial flow process and what is the interlink between the electrical and the mechanical component over there, and then you talk about the national policy requirement. Then you highlighted the very 6 basic point or strategy required for efficiency in industrial motor system. Then you cover digital motor system and why they are needed, like conditioning, remote control, load control, and the digital twin. Then you talk about the digital sensor for monitoring. So it was a very good. I think the participant also enjoyed a lot. So I have few questions over here. Let me. Yeah. Israd Hussain is asking why downsize the motor if actual demand is high. It may overload the system and shut down it when there is full load.
Thank you. Good question. Maybe I didn't explain it precisely. The motor is sized for 100% load, which means the nominal speed and the nominal torque. The motor 100% nominal output is what the motor can easily do without damage. It can do it for 1 hour or for 1,000 hours without interruption, and it has the highest efficiency about at the 100% point. Never undersize a motor. This seems to be the part of the question. You don't need 100% motor when you have 120% load. That would be an undersized motor. I didn't talk about that. I talk about 100% motor that during the week, during the year, never reaches more than 30% or maybe 50% of the load. We have monitored many systems, pumps and fans and compressors and mechanical systems that always run, let's say, between 20 and maybe 40% of load. 20 and 40% of load means for the motor easy, but it has a bad efficiency. You could cover the same load with a motor half the size or even a third of the size. Instead of a 11 kilowatt, you can use a 5 kilowatt, or you can even use a 3 or 4 kilowatt motor. This is what we call downsizing. It's not oversizing, but sizing to the necessary load.
Thank you for your response. Mr. Asif Khokar is asking, does condition monitoring can be carried out by third party, develop their own software other than manufacturer?
I'm not sure I got the question right. Can you show me the question in writing?
Yeah, okay, let me.
Can you put it in the chat that I can read it?
Okay, we are sending you in a while. Maybe he's asking, suppose some manufacturers you are using some product, and can third party develop that conditioning maybe?
I understand. I want to quickly explain. Condition monitoring is a general term. You can do condition monitoring by having a guy check every hour the motor, look at it, put the hand on it to feel whether it's hot or vibrating, and check the electric power. Or you can do it with an electric device, or you can do it by remote control. There are systems available from all the large manufacturers that you can build in at the moment you buy your new motor. Then they are part of the control, and then they have their respective software. But you can also use a third-party software or the electrical device when you have, let's say, you have 3 different kind of motors installed in your factory from different manufacturers, but you want to use one condition monitoring system for all of them. This is easily possible, should be no problem to apply that.
Okay, thank you.
Maybe I have some comments because I may have to forecast my presentation maybe on this Friday, because I'm going to introduce the International Industrial IoT Protocol, which is OPC-UA, which targets to solve this problem, because manufacturers, they will of course provide their digital solutions, and we would like to invite them, or we hope them to open the some access to us, to third parties, to the factories, to access the information. It's because the infrastructure, like the sensors or maybe even the gateway already there. Then we want them to access them or control them via some internet work. I think that's quite important. I think that also the trend of international development. I think that's what I'm going to introduce. I think this Friday morning, and next Friday morning, maybe, yeah, Friday afternoon, I think. Yeah. Okay.
Okay, thank you, Mr. Hugo. Dear participant, while sending the question, you can mention your country so that will be clear from where you are. Now, another question from Dr. Muntajir Hussain is, how can we improve the stability of heavy motor?
Can you please show it on the chat again?
How can we improve the stability of heavy motor?
I don't understand. AV, what is AV?
Stability.
Every. How can we?
Heavy. Not heavy. Big.
Every motor. Well, yeah, guys, the stability of a motor depends on the load. If you have a very, let's say, vibrating machine, we have been using our audit system in a stone quarry. A stone quarry cracks stones and make from the big stones, small stones, and eventually something like sand. And there you have a very unstable mechanical side at the output side of the motor. And the motor has a problem because it has a huge variation of torque needed and also speed needed. You can have a stone that gets stuck and blocks the system, but this machine still has to crack it. Therefore, there's no general answer, and I hope you mean the problems that I just mentioned. When you have a fan and when you have a pump, you have to work towards having the fan and the pump and the compressor run smoothly. If they run smoothly, your motor runs stable. If the motor and the pump is best oriented, use a laser to make it stable, then you don't have problem with stability of the motor. And when you don't have, let's say, vibration that comes from a secondary use, the motor is prone to being unstable if you have a highly unstable application. There you have to use both sophisticated sizing of torque, that you have a huge torque at the start, and you have to use a variable load, variable frequency drive to overcome such a blockage, and then you can operate it, let's say, smoothly, even if it's an unstable application. It's a very general answer I'm trying to give, but I hope that will more or less satisfy. Our experience is when you have appropriately sized motor, high efficient motors, everything is organized as it should. That means the motor and the pump is fine in parallel and the motor base is stable. Then you have a stable operation, and don't forget that the motor needs some grease once in a time.
Okay, that's all right. Thank you. And we have a few more questions. Chiranjeevi Jha is from Nepal. Is asking why repair cost is higher for small kilowatt motor.
You have to say it again. Why?
Why repair cost is higher for small motor?
Please write it down. Your acoustics is not so good. I don't want to answer the wrong question.
Please, we have sent you the question. You can check it, please.
Okay, now I got it. This is a misunderstanding. The repair cost. Yeah, I think maybe I didn't say it right, or I confused it. A small motor is cheaper to have it replaced. The high motor can be repaired because there are some what we call sunk costs. A 50 or 100 kilowatt motor is not just a piece you get from the shelf. It's maybe a little bit customized when you order it. It's maybe built into a machine of larger size. And there it's maybe I say worthwhile after 10 years to take the rotor out, to rewind the stator, to make sure that your bearings are okay. Therefore, the limit below 10 kilowatt replace, above 10 kilowatt maybe repair. Sorry, I caused some confusion here.
Oh, okay, thank you. And Mr. Nidu Chiring from Bhutan is asking, can the aging of motor be improved by the use of VFD?
That's a
Aging of the
complex
life
question.
of the motor. Can the life of motor be increased with the use of VFD? Is asking.
I got it. I got the question. I'm trying to find a good answer. Usually, a fixed speed motor, a small one, has a life expectancy, technical life expectancy maybe of 10 years, and a big one of 20 years, maybe 30 years. The VFD itself has maybe a lower life expectancy because of the electronic components, maybe only lasting for 10 years or 15 years. That means in a large motor, it can happen that you need for the lifetime two VFDs, one after each other. It's not so bad because there's also some technical improvements after 10 or 15 years. When you run a motor at fixed speed, that means the rotation is the same, but it can still have a variation of torque because the load might still vary. The motor can be stressed or overstressed, of course, and this can diminish his life expectancy. Also, a motor only operated at fixed speed, you have to make the load control by on-off. You make it on, off, on, off. This is usually okay when you have a fan or maybe a pump, but it's not so easily okay when you have a compressor. Compressor doesn't like to get shut off 10 times an hour. It likes to get shut off twice a day, something like that. Therefore, when you use a variable frequency drive for all these machines, you can operate the motor more continuously and vary the load maybe between 30% and 90%. And this is a very smooth process where the motor doesn't suffer frequent, hard changes of torque he has to deliver. And also the subsequent element like the compressor doesn't suffer from that. Therefore, maybe you can say a well-sized variable frequency drive in a well-sized motor can improve its age. Yes.
Yeah, thank you. Maybe we don't have more question now. So, dear participant, Mr. Wu, are you there?
Yeah, that's
Yes, I'm
a
here.
very clever question. Congratulations, very clever question. I make a simple example, just from top of my head. You have a 20 kilowatt motor and its efficiency, nominal efficiency is maybe 92%. And I told you have to replace it with a half size, a 10 kilowatt motor, and the 10 kilowatt motor has a nominal efficiency of 90%. Therefore, I'm telling you to go from 92% to 10%. This is the core of the question. That means that cannot be the case. You have to compare the bigger motor, which has a big nominal efficiency, to the actual efficiency he has at the respective partial load. The 20 kilowatt motor with 92% efficiency at nominal load operated at 10 kilowatt only has maybe an efficiency of 85%. And when you replace it with a 10 kilowatt motor with 90%, you're very much better than the 85. I'm just quoting the numbers from the top of the head, but maybe I was able to explain. Downsizing to a smaller motor reduces the nominal efficiency from the top bigger one to the smaller one. Yes, but you have to compare the actual efficiency at partial load under operating conditions of the larger motor to the smaller motor. Then you see there is a benefit when you go to a properly sized motor that runs basically between 70 and 100%. 70% is up to 100% is the optimal range of performance for every motor.
Okay, Mr. Kunar, we don't have more question. So thank you very much for your excellent presentation. So, dear participant, now we'll have a short break. Then at 3:30 Pakistan time, we'll join again. And there will be Mr. Roll Triben. I will be presenting on motor system efficiency and check with Modeline tool. Until that, stay tuned. Okay, thank you.
Thank you.
Okay, welcome back. So now we are moving to next slot that will be covered by Mr. Rod Tybin, and he'll be taking us through some tools, software tools. For your reference, participant, we have uploaded those tools in our website, as well as we have provided you in the chat box. And Rod Tybin has received his diploma as mechatronic engineer at the Technical College of Wilhelmshaven. In 2012, he joined SAFE, the Swiss Agency for Efficient Energy Use. He is founding member of Impact Energy, where he is a board member now. Impact Energy is an independent consultancy on energy efficiency in the industry, commercial, and agriculture sector in Switzerland. So with this, you may go with the presentation. Over to you, Mr. Rod.
Yes, thank you very much. So, can you see my slides full screen?
Yeah, perfect.
Good. Thank you very much for the introduction.
But
yes,
you can make it bigger.
sorry.
So in slide mode, so kindly to switch the screen.
So it's not full screen. Yeah, I see it. So maybe it's better this way.
Yeah, now you can just make it. Yeah.
Yes, now fine.
Okay, good. So I will close this and I will close this. Okay, so now it's better, full screen?
Yeah. It's
Good. Good. Okay. So thank you very much from my side for the nice introduction. I would like to present you how to optimize and analyze motor-driven systems and how big are the savings potential. We go in some theory about fans and pumps and so on. And afterwards, I would like to show you some tools. You can use these tools to analyze motor systems and have a systematic approach to find the biggest saving potential in energy or in motor-driven systems which you are analyzing. So as you already heard, my name is Rolf Thieben. I'm a mechatronics engineer. I was born in Switzerland and live in Germany and live in Switzerland now. And I am also the program leader of Top Motors, which is the information platform for efficient motor-driven systems in Switzerland. I would like to show you the content of today. First of all, I would like to show you some background about the energy consumption of motor systems, like Conrad already did, with a little bit different numbers or yeah. And also I would like to show you the findings of a financial incentive program from Switzerland, which is called EASY. We will talk about efficiency and efficiency chains. We will also define what is an electric motor system, where does it start, where does it end, and we will talk about different applications like pump, fans, VFDs, and transmissions. And we will see how big are the saving potentials of all these components. And in the end, we will have a look at the SOTEA and ELI tool, and I will show you the motor systems tool. So first of all, I would like to show you this pie graph, which shows the global electricity consumption worldwide. And as you can see, 46% of the diagram is for electric motors. Only the rest is for lighting, heating, and so on. So this means motors have a very important role by the energy consumption worldwide. And we had a look at the electricity consumption of these motors, and we found out that the most important or the biggest consumer of the electricity amongst the motors are pumps, fans, compressors, conveyor belts, and processing machines. So this means 46% of the overall consumption is for electric motors. We had a closer look to motors in industry in Switzerland. We analyzed 25 companies with a total energy consumption of 690 gigawatt hours per year. And we found out that 606.7 gigawatt of these total 691 was consumed by electric motors. In percentage, this means 87.8% of the whole energy consumption was used by motors. Only the last 12.2% were used by lighting, by communication, by canteen, and ohmic resistance like heatings and so on. So this means the far biggest share of the energy consumption was caused by motors. And that's why motors are so important to have a close look and to analyze and to optimize. So we did some analysis in Switzerland, and in total we analyzed 4,142 motors. And these motors were split in several parts. 34% have been fans, 22% have been pumps, 50% rotating machines, 11% for cooling compressors, 11% for air compressors, and 4% for others. And we had a closer look at these 4,000 motors, and we checked what was the nominal power, what was the average load factor, do they use a VFD, and so on, what was the age of the motors. And I would like to show you some findings out of these analyses. Here you can see a lot of dots, several thousand dots, which means every dot is one motor we analyzed during our financial incentive program called EASY. And you can also see a red line. And what this line means, I will explain soon. So first of all, we have the motor age on the left side on the y-axis, and we have the output power with logarithmic scale from 10 watts to 1000 kilowatt on the right corner. And you can also see the red line here, which is the operating life expectancy. It starts with 10 years below between 10 watts and 1 kilowatt. It's making a step upwards to 12 years between 1 and 10 kilowatts. 10 to 100 is 15 years, and above 100 kilowatt, it means 20 years. So this means if you're planning a motor system, you expect to work or to live for this time the line shows. So this means the small motors are expected to work, to operate, to live for 10 years, and afterwards they have to be replaced. The little bigger motors, 12 years, 15 years, and the big ones are expected to operate 20 years. So what this also means is every dot which is above the red line is already older than its expected lifetime. So as you can see, we have several dots with 30, 40, even 50 or more years of age. So this means the motor is working, is running day by day as it was planned 20, 30, 40 years ago. It also missed the technical development in motor technology, in application technology, was probably rewinded several times, had a lot of repairs and maintenance and so on. So this means the actual efficiency of the rewinded, repaired, maintained motor today is probably lower than its nominal efficiency when it was bought 30, 40 years ago. The total conclusion we found out was 56% of the analyzed motor were already too old, which means above the red line. And we had a look how much they were too old, and in average they were 99% too old, which means they are twice as old as they are expected to become. So if you sum it up, you can almost say almost every second motor was twice as old as it was expected to be. So this is a good point to have a look at motor systems also in Switzerland, to say, okay, we have a lot of old motors, we need new ones which are proper sized for the demand. If you have a 30-year-old motor, probably nobody ever checked after the beginning of the motor operation what the process really needs, what are the real demands and so on. And they're probably working like never touch a running system. And if it's running, it's fine. So don't touch and make any problems. We also had a look how much motors already have in VFD. And we found out 19.8% of all these dots, which are the 4,142 motors, already have in VFD. Every dark dot is a motor with VFD, and every light yellow dot is a motor without a VFD. Same here, we have the age on the left side on the y-axis and the nominal power on the x-axis. So as you can see, we have many motors which are pretty young. I would say less than 10 years have a VFD, but a lot of the older motors, which means here in the higher part of the diagram, do not have a VFD, which makes sense. VFDs are pretty new, I would say, not new like 5 years, but 10 to 50, maybe 20 years, but not 40 or more years. Also, it makes no sense to use a VFD, a modern new VFD, and put it on an old motor, which is 30, 40 years old. You have to check the application, the process. You have to resize and to arrange all components to each other. And if you just take an old motor, which is 30 years old, and add in VFD, you will probably get problems with the insulation. Old motors have a weaker insulation in their windings, and so the VFD can cause problems and shortcuts in the winding. So it's never a good idea to just add in VFD to an old motor. It's always a good idea to make a system approach. We also did some measurements and checked where is the load factor of the motors. By our definition, if the average load factor is less than 60%, it's defined as oversized. And as you can see here in this diagram, we have measured 104 motors, and we have the load factor. We have the load factor on the left side on the y-axis, and we have the nominal power again on the x-axis, logarithmic scale. And as you can see, we have a lot of motors which are in the lower part of the diagram, between 50–60%. And we counted these points and calculated that 68% have an average load factor of less than 60%, which means by our definition, it's oversized. So all these motors below 60% average load factor should be analyzed and should be checked. Do I have the right motor size? Do I really need that big motor? Do I have the right application like pump or fan or whatever it's driven by the motor? And does my process really need that much water, air, whatever? So if you start with a system approach, I will explain later what the system approach is of a motor system and what a motor system is, definition. You have the possibility to gain the best energy savings, or you can reach the best increasing of the total motor system efficiency. So to sum up, our key findings from our financial incentive program: 56% of our analyzed motors were already older than their operating lifetime expectancy, 10 to 20 years, depending on their size. 2/3, exactly said, 68% of the measured motors have been oversized, which means their load factor, average load factor, was less than 60%. Only 20% already had in VFD, we believe and we expect that 50 or even 60% of all motor-driven systems can be driven by a VFD in a good way, which means you will use less or even much less energy than before in an uncontrolled fixed speed condition. We also found out that motors are rarely designed to meet the real needs of the process. Konrad already mentioned in his presentation, there is an historic behavior to calculate some fear. Nobody wants to be in charge if the motor system is not starting or not working properly, is not fitting every possible need the process has. And so everybody is adding, I would say, a short percentage of fear to be sure the motor system is working. And the result is the motor system is working, but it's working in a very bad load factor, which means the efficiency in that point is not ideal and could be better. We also found a lot of qualified staff, which is available in companies, but they are not experienced yet in the optimization of motor-driven systems. So they are very good in their daily business, like maintaining or producing or whatever, but they are not experienced, and it has no high priority to have a look at the motor system in the efficiency, with the efficiency component or the efficiency point of view. And we had a lot of good examples in Switzerland where the saving potential of improved motor systems have been 20 or even 30% or more through our results during EASY. I will also show you later some more details about it. So Konrad already showed you this diagram with these 4 lines, IE1 to IE4. That's why I will just give you a short information. As you already know, IE1 is the lowest efficiency, IE4 is the highest efficiency. So it's always a good idea to buy or to start with best available technology, which is in this case IE4 motor, sometimes IE3, depending on the size and on the cost and so on. But you will have better nominal efficiency if you buy a very efficient motor. That's one big advantage. And there's another advantage. In this diagram, you can see 2 curves, a dark green one, the top one, and a light green one below. And as you can see, as you can see, the dark green one is okay, let's start here. So the X axle is a load factor. 1 means 100%, 1.2 means 120%. And this is efficiency, 0 to 100%. And as you can see, the dark green curve, which belongs to a modern IE4 motor, is very stable and very high. So you can see even here with 40% load factor, it's pretty constant and pretty high. If you go below 40, then the efficiency of the motor is dropping, and it's dropping pretty dramatically somewhere below here, which is no good operation point at all. Compared to the light green one, this one below, it belongs to a non-IE motor, which is a pretty old motor. And as you can see, the efficiency is overall lower, and also it's dropping earlier, which means around 50–60%. And the decrease of efficiency is pretty dramatic. So this means if you use an IE motor, an efficient motor, you have a very wide load band where you can operate your motor system very efficient. I would say from 40 to 100 or 120%. If you use an old one, you are overall lower, and your efficiency decrease is starting earlier. So your bandwidth where you can operate your motor system efficient is not that wide compared to an IE motor. Now I would like you to have a guess. I have 2 questions. The first question is, what percentage of the life cycle costs of a motor are energy costs. You don't have to write it down, just think in your mind, is it 50%, 60%, 90%, 99%, whatever, and just have a guess how much or how big the percentage of the energy cost of the lifetime cost of a motor is. And the answer is, it's 96.7%. You can see the pie diagram over here. The whole pie diagram is the life cycle cost of an 11 kilowatt premium motor IE3 during 15 years with 4,000 hours operating per year. And if you have a closer look at the total life cycle cost, you can see only 1% is for maintenance, 2.3% is for purchase price, and 96.7% is for energy costs. So this is why it's so important if you have a motor, big motor with many operating hours, you will use a lot of money for energy. And if you can improve your system only by 1, 2, 3%, it saves you a lot of money, and it's pretty economic. If you do improvements, you will reduce your energy consumption and saves you money. Will save money for the costs of the optimization during the lifetime, or even pretty fast. My second question is, within how many operating hours the energy costs as much as the purchase price of a motor? So this means how many hours does a motor have to operate until he uses energy costs which are equally high as his purchase price? And the answer is within 1,200 hours. So within 1,200 hours, which can be only some months, the motor has used so much energy which costs the same as the purchase price of the motor. That's another important point why it's so important to have a look at the overall life cycle cost, and also especially the energy cost, and why efficiency is that important. So with an efficient motor, you can save money, you can increase the reliability. Konrad explained earlier, you reduce the risk of failure. You also reduce peak loads of the electrical power and consumption, which costs a fee in Switzerland. If you have a high peak load where you take a lot of nominal electric power from the grid, you have to pay a fee in Switzerland. And if you can reduce these maximum power, you will reduce your fees, and this can also save you a lot of money. You can also reduce environment impact depending how the electricity is generated. Often it's by coal or nuclear, and you can also use it to improve the good image of the company. So if you have a company which wants to have good public relations, energy efficiency projects are always too good to have good PR. So I've talked a lot about efficiency, but what is efficiency? Efficiency is the ratio between output power and input power, which means output power divided by input power. As you can see in the lower part, here we have a rating plate from a motor. It's a Siemens motor, but it doesn't matter. As you can see, it's 50 Hertz, it's 7.5 kilowatts, cosinus phi is 0.92, and he is also given the efficiency IE2, which means 88.1%. So now, you do not always have the efficiency given on the name on the rating plate of the motor, and sometimes you have to calculate. First of all, you have to know these 7.5 kilowatts on the rating plate. Is it output power or is it input power? It's an important fact to know. And I can tell you, it's always output power. This is the nominal power at the shaft, at the nominal current from with 13.4 amps in this example. So this means if you put 13.4 amps of electricity of current in these motors, you will get 7.5 kilowatts at the shaft. But the motor has an efficiency, which means it has losses. And this also means you have to feed the motor with more input than to compensate the losses. So this means if you want to calculate the electric input, you will have to take the nominal output, which is 7.5 kilowatts, and divide it by 0.881, which is 88.1 efficiency. So this means you have to feed the motor with 8.5 kilowatts electrical power to get 7 kilowatt output power, mechanical output power at the shaft. Sometimes, or often, it depends how old your motor is, you do not have these 88.1% given on the rating plate. Then you can also calculate the electrical input power by all the other values on the rating plate. So if you multiply 400 volts by the nominal current, which is 13.4 amps, multiplied by cosinus phi, which is 0.92, multiplied by root 3, you get also 8.5 kilowatts. So if you do not have the efficiency written on the rating plate, you can also calculate the electrical input power which is needed to operate at the nominal 7.5 kilowatts at the shaft. This also means if you know the 7.5 kilowatts mechanical power and you calculated the 8.5 electrical input power, you can also calculate the efficiency, which is in this case 88%, which is in this case also given here. So if you do not have the efficiency, you can calculate the efficiency pretty easy. If you, in this case, it's the result of the 7.5 nominal output power, which is given here. Always remember, it's the output power, not the input power. And the input power can be calculated with this formula. And so you get two different powers. And if you divide these two different powers, you will get the efficiency. So I am always talking about motor system, but what is a motor system? So in this picture, you can see we have a motor-driven unit. And when we talk about motors or electric motors, normally we mean motor system. And a motor system is, by our definition, not only the motor here in the middle, it also contains a VFD or a soft starter or whatever. It also contains mechanical equipment like gears or belt or clutches, brakes, throttles, whatever. And the application, of course, which is a pump, a fan, a compressor, and so on. And this motor system is delivering to the flow. And how can you optimize your motor system in the best way? So the best way is to start from the end. You have to have a look at your process, at your flow. What do I really need for my process to fulfill all needs? And if you know your needs, you can resize, you can dimension all your components to the proper size and make it fit perfectly to your process. So this means you have to evaluate the required flow, pressure, time, and so on of your process. You should use best available technology for pumps, fans, compressors. You should try to avoid mechanical equipment like transmissions. I will show later some belts or some examples for transmission belts and their efficiency. And you should also avoid throttles. If you have a fixed speed motor systems and you want to have an influence to the, let's say, airflow, you will use some flaps or something like that to reduce the flow if you not need the full flow. But the better way is to use a VFD to make the motor turn slower and save energy. How much energy we can save, I will show later. So try to avoid throttling and transmissions. Use IE3 or IE4 motors, why I already explained, and use load control whenever possible, whenever useful, to make a system turn as slow as possible to fulfill the needs of the process. And why is it so important to have a look at all components with all their efficiency? Because we have an efficiency chain, and all efficiencies of all components are multiplied by each other. So it's not added 1 + 1, it's always multiplied by each other. And this also means if you have a component with a very bad efficiency, like say here, fan area, it's 20 to 80%. If you have a fan which operates very low, 20, 30%, every other component is also multiplied by 20, 30%, whatever. And this means your system efficiency is dropping very, very low, less than 20 or 30%. If one efficiency is 20%, for example, the total system efficiency has to be lower than 20%. It can't be higher than the lowest single efficiency. So this is why it's always important to get the best efficiency of all components by using best available technology, and also by reaching the best operating point for the application and for the component. We've heard a lot about VFDs. VFDs are great. VFDs are to vary the speed of electric motors. So in this case, we can reduce the flow. My example shows a fan. And the big advantage of manipulating the flow by manipulating the speed of the motor is we can save a lot of energy. So physics is pretty good in this case. It helps us to have a lot to reduce the energy consumption by big percentages. And there are also some negative points. We have some positive points, which means we can regulate, we can make ramps to start or stop systems and so on, and also we can reduce the flow. But there are also some disadvantages, like additional losses. First of all, the VFD has additional losses, 96 to 98%, sometimes 95%, it depends. And also it's causing harmonics, which means to reduce the efficiency of the motor a bit. So there's another disadvantage. Harmonics itself can be a problem if you have several VFDs. Maybe you need some to compensate that, and so you have to check when you're planning motor systems with VFD to make sure the VFD side effects are not having a bad impact on your process. Also, VFDs have a very poor efficiency at low load, which means, again, you have to resize it properly to have a pretty high, as high as possible load point to have the components in best efficiency, and also the VFD. And the VFD has additional costs. It costs around the same purchase price as the motor itself. And as Konrad already mentioned, a VFD lifetime maybe 10 years, motor maybe 20 years. So this means you need 2 VFDs during the lifetime of one motor. Okay, so I would like to show you how you can use a VFD and how it's used in the older days. So the top part of this image shows you full electric power, a motor, a fan, and full cooling, which means this is a fixed speed motor running at full speed, 100% RPM, and you're using the full cooling. If it's necessary, it's a perfect way to use it and to do it. But in most cases, you do not need full cooling the whole time. So you can use flaps like this to reduce the cooling, which means the motor is still working at 100% speed, and the flow is still 100%, but you only need, like this example, 2/3 of the flow. So 1/3 is guided by a flap away from the process, and it's not used at all. There are better ways to reduce the speed and to regulate the flow, which is in the lower part of this diagram. We have reduced electrical input power, we have a VFD and a motor, and we have reduced cooling. We get this reduced cooling by a slower speed of the motor. The VFD is reducing the fan speed, and that's why the motor or the fan is only providing a reduced amount of flow and a reduced pressure. And in this case, I can save a lot of energy. How much energy it is, you can see in this diagram. It's a pretty important diagram, so that's why I will show it twice today. On the x-axis, you have 0 to 100% flow, which means 100% speed of the motor equals 100% flow of the fan. On the y-axis, you have the electrical input power from 0 to 100 or even 104%. You have 3 curves, red, purple, and blue. The red curve means the electrical input by throttling. If you use flaps or something else to choke your flow, you can reduce the flow of your fan system up to or down to 0%. So this means there is no airflow at all, but your system will take still 50% of energy. So you will no use at all from the flow, but 50% energy consumption of the motor. If you have a look at the purple line, this is your energy consumption by the users of a VFD. So this is what your motor and VFD combined will use if you reduce the flow. So this means if we reduce the flow to, let's say, 75%, we will meet this graph here, and this equals something like 55% energy input. So by reducing 25% of flow, we can save almost 50% of energy. The difference between the blue line, which are the losses by the pipes, is the efficiency of the VFD itself. You can also see at 100% flow, you will use 104% input power, which means you have to put in the additional losses for the VFD. So to reach 100% of flow, you will have to put in 104% of energy. So in this case, whenever you are above the red line, you will lose money or waste money or whatever. But whenever you are below this red line, you will save energy. And the saving potential is the green arrow here, is always the difference between the red line and the purple line. So depending where your new operating point is, you can save a big amount of energy and also a big amount of money. So that's why especially fan systems are pretty good to be driven by VFD, because there is a huge saving potential. And the saving potential is here is power equals flow root cubic, sorry. So this means if you reduce the speed by 10%, your energy consumption is 0.9 times 0.9 times 0.9. And this means you have only, I would say, 70% energy input left by only 10% less flow. Okay, so as you have already seen, a motor system contains a VFD, a motor, transmission, and an application. I would like to show you some information about applications, in this case belts. There are also a lot of different types of gears, but we do not have the time to talk about gears today. So that's why I will just focus on belts. Here you can see a very old machine in Switzerland with a lot of leather gears, belts, and pretty old, pretty historic. That's not the actual state of today. But there are still belts in industry and pretty common, and these belts are necessary most of the time. Sometimes they are unnecessary, then it's better to avoid it and to not use it anymore. Here you can see the three different belt types, which are pretty common and pretty often used in industry. We have V belts, which is the most easiest and robust one. We have flat belts and toothed belts. And the difference between V belts and flat belts can be divided by these categories here on the left part. The mounting of V belts is pretty easy. It doesn't matter if it's aligned pretty properly or not. As I already mentioned, they're pretty robust, and the alignment is no big problem at all. If you use flat belts, the mounting is very challenging. You have to use laser alignments to align the axis and so on, because it has to be very clean, very smooth. Otherwise, your belt will run off your pulley and cannot transmit any forces at all. We also have tooth belts. The mounting is a little bit easier, not that complex like compared to flat belts. Also the difference between these three are V belts have to be retensioned several times. It depends on the products, but in general you have to retent. You have to retent in frequently times. Flat belts, an advantage, no retentioning necessary, and also the tooth belts, there's no retentioning necessary. Sorry. I also showed the most important facts about the environmental impact, like noise and abrasion, the pollution. If you use I would say a fan system in a hospital, you will rarely find any V belts, because V belts have a lot of wear during their operation, and the wear is in their air systems. And if you need a very clean environment like hospitals and so on, you do not want to have wear in your air. So in that case, you will rarely find V belts. They will use other belts or even avoid it if possible, and so you can avoid the pollution of the air by the belts and by the transmission. Yeah, I think we just go on. Belts and transmission also have an efficiency, which means they create losses. In this diagram, you can see 4 lines. The blue lines are flat belts. Blue line with a circle means 80 to 100% load, and the blue line with a triangle means the bad operating point, 20% load. And as you can see, the flat belts 80 to 100% has the best overall efficiency. We have the nominal powers here from 1.1, which is 100 watts, to 100 kilowatt. That's the transmitted nominal power of the belts, and we have here the total efficiency of the transmission, starting 75% up to 100%. And as you can see, the flat belt 80 to 100% has the best overall efficiency. Operated at 20% load is a little bit worse, but still okay and still high. The red one is a V belt, also with the circles. It means 80 to 100% load. You can see it's starting also pretty high, and it's dropping somewhere here with lower loads. So this, yeah, so you can see V belts maybe are not the best solution for small loads. And also you can see if you use a V belt in partial load, in this example 20% load, you will get a very bad total efficiency of around 87 to 80 or 78%, which is pretty low. Remember, if you have a bad efficiency, it's multiplied by all other efficiencies in your system, and that's why it's having a good, bad, or big impact if you have for one very bad efficiency. So in this picture, you can see losses. Losses are just heat, and these are pictures with a thermal camera taken. And on the left side, you have a V-belt with two temperatures measured, SP1 and SP2. SP1 is 33 degrees, SP2 is 32.3 degrees. On the right side, we have the same test with a flat belt, and as you can see, the same conditions transmitted with a flat belt causes lower temperatures, in this case 16.3 and 16.9 degrees. So you can see the flat belt has much less losses within the belt. If you use a V-belt, you always have you always need a lot of force to bend it around the pulley, to push it in the pulley, to rip it out of the pulley, and that's why it's causing a lot of friction, internally friction, and also with the pulley, and that's why they have a worse efficiency compared to that flat belt, which is wide and very thin. Here are two more pictures also taken during a test. We have one flat belt in the top left corner, a normal picture, and the thermal picture of that test bench. And the temperature is around 35 degrees. And the same application with 1, 2, 3, 4, 5, 6 parallel V-belts on the same test bench causes 50 degrees in the transmitting belt. So this is, yeah, so this shows the losses of a transmission, in this case the V-belts. Konrad showed in his presentation this picture already, a fan system. I would like to talk about fan system, and this is just one example for a possible fan system. We have the motor with pulley, transmission belt, a V-belt in this case, and we have the fan itself. Normally during operation, you just close the door and it's working 24/7. In this case, there is no VFD, so which means it's either on or off, 100% or no, 0%. There are different types of fans depending on the process and on the need you have to your fan system. There are axial fans, which are pretty easy, pretty common. There are radial fans with spiral casing. They are subdivided by forward curved blades and backward curved blades. In general, backward curved blades or fans with a backward curved blade do have a better efficiency compared to fans with a forward curved blade, but there are some differences in the sizes and so on. So if you have the size to use backward curved blades, you will get a better efficiency compared to forward curved blades. But these are pretty individual cases. You have to have a look with your expert, with your fan expert, and check, do I have the space to build in a bigger fan with better efficiency, or is there only a tiny space where I can mount my fan? There are also some modern new versions of fans. This is the radial fan with direct drive. As you can see, these are the blades of the fan, and this is the motor, and it's already equipped with the VFD in it. So it's one part containing the fan itself, the motor, and also the electronic. And this has a very good efficiency, and it's more or less now state of the art in fan technology. And these typical fan systems, like these radial fan systems, get renewed by these EC drives, And normally it's like this. If you reduce a big radial fan, you will use several smaller EC fans, I would say 3-4 EC fans. So this gives you also the advantage of redundancy. So if one of your spiral fan fails, you have 0% air. And if one of your, let's say 3 or 4 EC drives fails, you will still have the other 2 or 3 fans, yeah, depending on the example. So that's another big advantage of the redundancy. How can you optimize your motor systems? As Konrad also mentioned in his presentation, there are some steps and some checks you have to do. And the most important step of all and the biggest impact is to choose the correct flow, the volume flow. What does my process really need, and when, and how long? That's this most difficult question, I would say. And if you know your process, you can exactly choose your components of your motor systems. You have to know what flow do I need, what speed do my air has to have, what channel size, if you can change it. If you just replace the motor or the motor system, the channel size is normally fixed, but if you optimize the whole ventilation system, maybe you can have an influence on the channel size. Operating hours, do I really need that flow during night, or can I stop for several hours, or can I reduce the speed to a very low speed to save money there? You should use sensors in your room or in your production facility to measure the temperature, the humidity, CO2, dust, whatever is important for your process. And this gives you always a good value to regulate your VFD. So your VFD will always let your fan slow as fast as necessary, but also will slow down as low as possible. And with a variable flow, you can always meet the needs of your process, but you will never waste any energy by converting more flow, more air than necessary or than needed. If you, especially in fan systems, if you change a motor, let's say, for example, IE1 to an IE4 motor, you have to be aware that the new IE4 motor spins faster than the old one. As you can see here, we have on the y-axis the pressure of the fan system, and here the flow. We have the fan curve, which is here the black one, and the machine curve, the blue one. If you replace the old motor by a new, faster one, you will get a new operation point here in this diagram. This is the operating point after the replacement without the transmission adjustment. So this means you will have more air, more flow, and also a higher pressure, which can be good, but most of the time it's not necessary. But what this also means is you have to put more energy into your motor system to get this new operating point with more pressure and more air. In most of the cases, more air and more pressure is not needed, because if you sized your motor system properly, it fits perfectly to your needs, and that's why you do not need any more pressure or flow. So if you change your motor to a more efficient one, you have to compensate this higher nominal speed of the motor. If you use a VFD, it's pretty simple. Just change the setting in your VFD to the new nominal speed, and it's done. If you're using a fixed speed motor with transmission, you have to change the transmission ratio between the pulleys, which means you have to change the pulleys and the transmission, so the diameter ratio of both pulleys will change, and afterwards you will have the same nominal speed on the fan side than you had before with a slower motor. And what this also means is you push back your operating point to the actual point where it started. So if you change the transmission back to the, or you adapt the transmission ratio to your new nominal speed of the motor, your operating point will drop back to the point where it started and will deliver the same amount of flow, the same amount of pressure, but with less energy input of the motor. And that's when you save energy by using a new, more efficient motor. I just showed you this diagram and explained why you can save a lot of energy. But if you think about it, if you buy a faster spinning motor, you can also waste a lot of energy. In this diagram, I'm saying 3% more speed equals 9% more electric power. So just a reminder, I said I will show you this diagram twice because it's very important. If you do not adapt your transmission, your new operating point will be somewhere here, maybe 3% higher because of 3% more nominal speed of the motor. So this means also for the electric input, if you think this diagram will go somewhere up here, we are much higher than 100%. So this means we put a lot more energy in the fan system if we do not adapt the transmission. We also get more flow and more pressure, but as I said, it's probably not needed, and that's why you have to compensate. Otherwise, you will use more energy in a bad case than before. So how can energy be saved in fan systems? The easiest way is optimize operating hours. If it's not necessary to run during nights, weekends, holidays, whatever, just switch it off. If possible, always make sure it's okay to switch something off. But that's the biggest way, or the easiest way to get big savings without almost any cost. Another big impact has a VFD, a regulation. If you use sensors in your rooms or in your facility or factories or whatever, and you reduce the speed as far as possible, you can save a lot of money and a lot of energy. With the diagram I've shown before, there is a huge saving potential, which makes it easy to save a lot of money for the optimization costs. Resizing causes a good operating point. Good operation point means good efficiency of the application and also for the motor system. So the system approach is very important, and best available technology, especially by fans. Fans made a huge step in technology, in production. Nowadays, there are three-dimensional curved blades which are simulated by huge computers and so on, which haven't been there 20 years ago, where the curves or the blades have just been flat and so on. So there has been a huge step in technology, and that's also a good reason, or big reason, why it's always good to use best available technology. If you reduce the energy consumption of your fan system by reducing the flow, there are also additional benefits which we are not calculating in money or kilowatt hours, but we are always mentioning if we suggest some improvements, because every cubic meter you do not convey or deliver to your process, you do not have to heat or cool it, you do not have to filter it, you do not have to maintain the filters. We have less noise. Maybe you have a better climate comfort if it's comfort lifting a company for the employees and so on. So these are additional benefits, good arguments for your boss to get the okay for an improvement, but it's hard to calculate this in numbers like kilowatt hours, US dollars, or whatever. So Now I would like to talk about pumps. In industry, there are 4 major application categories for pumps. The first one is circulating, which is just conveying a fluid like water for heating or cooling in a closed circuit. Lifting, if you pump water to a higher level, like in sewage plants or in reservoirs and so on, you just lift it up from one tank to another tank in a higher level. Pressure increase, which is important for high building and so on. If you have to pump the drinking water up to 20th, 30th floor or whatever, you need a high pressure to pump the water there. And the last one, which has the smallest share of energy consumption, is transport. You just move a media mainly horizontally from one part of the production line into another line. I would say milk is a good example in industry. First of all, you cool it, you heat it, you whatever you process it and so on. It's on a horizontal line, and it's mainly for transport. And these application categories can be divided in 2 processes. It's one is a closed system and one is open system. The closed system can be compared energy-wise to a fan system. A fan system is always closed by atmosphere, and a closed systems by pumps means that water is pumped in a closed system for cooling or heating and so on. And what's interesting is if you have a closed system in a high building or whatever, the height you have to overcome it doesn't count at all, because on the other side, you can see in this diagram, you have the same pressure in this pipe than here, because it's always leveling itself, the fluid. So if you want to convey the fluid in this circle, you just have to overcome the pressure losses of the system. And how huge your pressure losses are is task of the planner. He knows all the pipes and all the lengths and all the bows and so on, so he can calculate the total losses of the pipe grid, and that's important to know when you are resizing or sizing a motor for a closed system. The other big advantage, as you have already learned 2-3 slides before, if you can reduce the speed in a closed system, like here, you will save with energy with a third potential, which means P equals Q cubic. Again, as I have said during the fan system slides, if you can reduce the flow by 20%, your energy consumption will be 0.8 times 0.8 times 0.8. So this is probably only a little bit more than 50%. So it makes a lot of sense to reduce the speed whenever it's possible. And in cooling or heating system, it's pretty easy with sensors to reduce the speed to the lowest level possible. But there are also open system, which is our example B here. This is an example. We have just some reservoir here and some at a higher level here. And to pump water from down below on a higher level, you need to overcome the height, the geodetic height. And this is the most important value for the power you need to overcome that height. There are also some losses because of the piping losses, the friction and so on, but they are pretty narrow compared to the energy you actually need to lift that water up to a higher level. How can you save energy? It's almost the same than in fan systems. The easiest way, biggest savings, optimize operating hours. Do I really need it during night, holiday? Can I switch off? Switching off is pretty cheap and very effective. Regulated operation with sensors, as I have mentioned, in cooling or heating processes, use sensors to reduce, I would say, the cooling flow to the lowest possible value, which is necessary to reach my given temperature I would like to have my process. For example, ideal temperature and fuel, ideal flow, as mentioned, color sizing is key to have a good system efficiency. To have a good overall efficiency and system efficiency. And again, use best available technology. Technology for most, and also like in this case for pumps. So systematic approach. Now we know how to optimize and what to optimize, and if you come to a company with, let's say, 1,000 motors, how do you know?
Hello, Mr. Rod?
Know where to start?
Mr. Rod? Hello? Your voice is broken, please. May we check it? Might be your internet is very poor over there. Can you message him?
Hi, Rob. I cannot hear you.
Yeah.
Hello, Rob. We cannot hear you. What's the problem? Network or maybe some equipment problem? We can see that you are speaking, but we cannot hear you.
Hello?
We cannot hear you. We cannot see you.
Yeah, maybe Mr. Rod is disconnected, might be. Mr. Hugo?
I think
Can you hear us?
Yeah, I can hear you.
Yeah, please. Hello, Mr. Rod? Mr. Hugo, can you contact him, please?
I'm trying to contact him via Skype, but I cannot
Okay,
reach
please.
him right now. Maybe that's network.
Can you continue now? Your voice is clear, I think.
This moment. Nice woman, not Rod. Okay. Hello, Mr. Rod. Are you with us now? Let's wait.
But still not reachable. Strange. How strange.
Hello, Mr. Rod. This is funny, kind of. This one. Is there? Hello. Hello, Mr. Rod.
What's the problem? I don't know. Maybe not a problem network. I talk, I send a message via Skype.
Uh-huh.
Still not reachable, and I think it's quite strange. So
If you have you have his contact number, then you can contact his mobile phone.
maybe I can continue with Rob's presentation because I know the tortilla and also for the rest a little bit.
So can you
Proceed,
continue?
okay?
Mr. Rambo,
I'll be
you
back
can
up.
continue.
Hello, Rob.
Yeah.
Maybe you can appoint me as the speaker, okay? I can continue, please. Okay.
Yeah, please go. You continue, please.
Okay, I will continue
Yeah.
this
Try
work.
to
Okay.
connect. If Rolf is
Can
there, then
you-
he will reconnect.
Can you see my screen now?
Yeah, perfect. Please go ahead.
Okay, so I think Rolf, always we think about the systematic approach because, the Top Motors program invented a lot of software tools. It's called Tortilla and also ED Plus. I think this is Tortilla. That's the Excel file I presented maybe begin earlier. Then from this beginning is the factory assessment. It will be used to, to initially to assess how about the potential of the motor system saving potential in your factory as an initial thought, because we want, first we have to invest, first we have to assess, then have to decide whether we'll invest more resources, especially for the management, the engineering, to do the work. And this is, Tortilla software. If you open the, the Excel file mentioned, you can change language, you can currency, data, company name, and also then you can fill in all the data that's needed, and then you can see calculate from this calculation. From this calculation, you can see this this factory has some energy consumption power here, and also the fraction of the different power sectors, and then finally you have a top motors, Tortilla energy system. Here is energy consumption. Here is optimized energy consumption. Here is saving potential. Then, if you can see, it has high saving potential. Here, you can see potential of energy efficiency in percentage. That means you have 11% of your efficiency improvement in your factory now in future. Now you can see that okay, if 11 is a good value, then we decided to invest to this kind of efficiency improvement. This is the first step. First step is to get a general understanding how saving potential in your factory of the motor systems. Okay, it's roughly initial thinking. Inputs quite simple, output quite simple. Finally, you have to make a decision. Does a systematic analysis of the motor system make sense for your factory? You decide to or not. Then you can calculate saving potential. It's roughly, it's roughly a tool. By just general assessment, you can determine the efficiency by the motor age. Like Karen mentioned several times. Also motor size, big, small, medium, motor, and also whether you use VFD or not, the VFD application rate. Then finally, you will see that the ideal state is use IE4 motors. The share of VFD should reach to 60%. 40% could be constant load, but for the rest, 6% supposed to be used VFD to reduce energy. Finally, you have some additional costs, better motors, VFD, and monitoring. And this is a customer input. Then you can see from the total energy consumption, you can gain the efficiency from right to left. Then you can gain the efficiency, also tap the energy consumption potential from the factory. Okay, that's the total electrical. And this is Sortia. I already mentioned Sortia. You have several steps. First, fill in the data, fill in the forms. Second is, let me check whether Rolf is back, because he is a person to prepare the presentation. I worked with him for several times. I know this more or less. And then you can get result. Result here, the most important is how much you can save. This is 11.5%. Okay, and then you can use some estimation. You can input some like the currency information, the electricity price, and also maybe some employee cost. Then you can make some initial assessment whether you would like to invest your engineers' time and also maybe some other financial resources to motor system efficiency in future. That's the initial decision tool. Okay, and second step is ELI Plus. ELI Plus actually is called the Smart Motor List. With Smart Motor List, you can get you can list all your data. You can list all your motors from the factories, and then you can change. You can select the most potential motor systems from your factory. You can see that from the inputs come nominal data motors could be the power and also the age, the operating hours, and also the VFD percent. Then it can make some initial calculation. Then you can get some result. The most important is identification of the biggest saving potentials. For the initial assessment from the motor list, you have some criteria to select the product, to select the motors. First one is age. The older the age, the higher potential, because older age of the motor, some low efficient technologies, and also operating hours, low operating hours, high saving potential, and also the VFD. You can use FD to change the system. And second is nominal power, big motor, big saving potentials. Then you have to follow the steps. First is the data connection. Then you can check standard values. Then you can calculate actual consumption. Then you can use second criteria for decision maker. And also finally, you can make a recommendation. Then you can see that whether it's worthwhile to invest in this kind of retrofit project of the motor system. And this is the language selection. This is when you open the Excel file. Then you have the choice of different languages: Deutsch, French, and also English, and also, because I'm working with them, have Chinese version. Of course, for you, you can choose the English version. Then, second, you have the interface of input, the menu. First, basic data. You can input some basic data. You can decision maker. So selecting criteria to select a product. Finally, you can get some result from the right side, and you can see. First, you have to input some basic information of a company, factory, building, something like this. who did this kind of filling of the motor, and also the energy consumption, and also even the electricity price. Then you can choose different currency from different countries. I think you can choose USD, and then you can use apply. Then this interface, you can input all the motors in your company or your factory. First one could be the the type of the plant, type of motor name, and also the manufacturers, the motor manufacturer, and also the identification number, and then the year, in which year. I think this is most important. In which year your motor is invested in use. This is one case from Switzerland. That means one motor, it was put into use in 1970. It has aged more than 40 years. And then age will be calculated automatically, and also the operating hours. If its operating hours is long, that means it has high shipping potential. And also here is application. It applicates to pump, ventilation, compressed air, also pump. Then you can decide which one you can use. And then you can and then finally you can see that the mechanical nominal power, the high of the power, and then the high of the shipping potential, and also loading factor. Rolf already mentioned the loading factor decides the operating efficiency of the motor. This is estimation. This is the loading. Actually, you can use some meters to measure this. And also number of poles. Almost, I think most of the motors are 4 poles, and also the efficiency class. And then finally, you can choose some. This is initial calculation result, the consumption, and also designation, shipping potential. Then you can use some kind of, this is selection criteria. If it meets some criteria, it will get 1 point. 6 means it meets 6 criteria. That means the higher of the points, the possibility of the product of the motor to be selected. Then you can see whether I will select this product to further analyze for test, also maybe for a specific testing. Then yes, means we will invest our engineering resources into this motor. And then you can use the decision maker. The decision maker is valued the data of 80+. It identifies greater shipping potentials from some initial calculation, and this will compare the motor data with selected criteria. And also it can can make different colors with different the motor. And then we can use the decision maker. See, after decision maker, you can see that we can set some criteria. This is the default values. This is our my values. It means first is shipping potential. Second, we want to select the motors elder than 20 years old. We want to select the motors operating 1,800 years per year. And also we want the motor be higher than 10 kilowatt hours, kilowatt, because the higher of the motor, have this high shipping potential. And then whether we can use a frequency converter, which is Vfd, then yes. And then we want to to retrofit the pump, the ventilator, and also air compressor, and also maybe conveyors, others. After this kind of selection, they can select the product from your list. This is a calculating result. This is the process. Identify motors for all optimization, because we have a lot of motors. I found one factory in China, it has more than 10,000 motors. We have to identify the most potential motors from the long list. And then this is slogan with it. 20% of the motors save 80% of the efficiency potential. We have to use a systematic approach, identify such kind of 20% of the motors. I think that's a process. That's the criteria. Then we can see some point meets. That means it meets 6 criteria, 3 criteria, 5 criteria. Then we can manually check whether it will be further analyzed. Yes, then we can export. We can filter the on and off. Then we can see we want to further optimize the kind of system. Then we can do further analyze. But export result and also make summary. I think that's the process of the. Finally, when you decide which motor to be optimized, we can use a multi-system tool developed by the U4E, not U4E, could be the IEA 4E electrical motor system annex. This is tool developed by Danish Institute of Technology. It's available and it's for free. It's online. You can download this, and also the guidelines are already there. You can use the guidelines, you can follow the guidelines, to measure and also to input the data. Then you can calculate the specific efficiency of the system. Then you can find a way how to optimize the system. I think that approach we follow. First, we make general assessment. Second is we use motor. Second, we use the smart motor list to identify most potential motors. Third, we use motor system tool to analyze the efficiency of the motor. There are a lot of knowledge behind such kind of tools. I think it's already available online. You can go to the website to get the knowledge, and also to understand what's something behind, because guidelines are provided free. You can experience by yourself. Of course, if you have any problems, you can send it back to me. You can even have some cases, and also they have webinar slides and also webinars to teach you how to use such kind of tools. I think also the top motor structure. On the website you can find the top motor structure. It's 10-page guided examples. There you can to get better understanding what we're talking today. And also if you have any questions, you can contact us. Then I think that's the result. And also you can contact Rolf directly, and also me, and also this here is three organizations: Top Motors, Motor Summit, plus Motor Systems. I think that's all from my side. Okay. Oh. I finished my presentation, and also I'm open to questions.
Yeah, thank you, Hugo, for your presentation. We have apology, dear participant, that Mr. Road disconnected because there was some problem at his end. However, Mr. Hugo carried over the rest slide. Yeah, Hugo, we have a few questions over here, and at the same time, you'll be getting this question in your chat box. So let me read it out. Mr.
I2 is 8% and I3 is 6%, which is more efficient.
Yeah, this is a question from Chering Chodin from Bhutan. Yeah, please.
Okay, I think that's a very interesting question. Currently I cannot see, I cannot give a really example, but I think from my understanding, I think it's supposed to be I2 with 8%. It's more efficient. 8% means load factor. That's right.
Maybe we move to next question, Mr. Hugo. Okay, so this question is from Dr. Khurram Parvez from Pakistan. So he's asking
if the motors are not properly balanced, how does it react to such kind of ifs? I think VFD itself is very important. The electrical equipment to to balance, or maybe to try to correct the imbalance of the three phase. Because I'm not an electrician, but I think maybe you can keep this question for tomorrow, or not tomorrow, that's for Wednesday. Andrea Vizzini, he is a professor from the university. He understands this question quite well, maybe much better than me, because I'm not an electrician. Okay?
Okay, thank you. Okay, Dr. Khurram, your question will be passed on to the coming presenters. So, can you find any other question, Mr. over there?
How much? Okay, I can see that. How motor efficiency could improve if used for 12 years? Could improve if used for 12 years of generate bearing, cooling, but pump for cooling, fuel quite costly. How motor efficiency could improve if VFD used for 12 years old generator bearing, cooling water, where cooling flow required continuously? I think it depends whether the load is changing, because if the load is changing with the time of the processing line, I think VFD can play the role of to change the speed of the system to adapt to the demands of the processing line. But if the load is constant, like many cases circulating constant, I don't think VFD can improve the total, not efficiency, maybe the energy savings, because when you apply the VFD, actually the efficiency of the motor or even the VFD might not be high, but it can reduce the load, it can reduce the demand. That's most important for the application of the VFD or the benefits. You don't have to generate so much kind of flow. They save the energy. It's not about efficiency. Maybe from my point of view, the efficiency might be reduced, but the total energy can be saved. Tomorrow I will show you, because I will present tomorrow according to my finding. Okay?
Okay. So,
What more else? Yeah.
you have any other question? Yeah, Mr. Hugo. What about that? This ILI, no? You were talking about these tools, the resource
It's Excel
thing.
sheet based. Yes.
So,
It's Excel sheet based.
how participant can use that? They are asking it is Excel based or some this software.
Yeah, it's Excel based. You have to install Excel first. Yeah, it's Excel based. So it use actually the VBA, the Visual Basic application to execute the program. It's a program actually. It's Excel based. No problem. Yeah. But the motor system tool is not Excel based. It's based on, you can install it in your computer for Windows. It's for LabVIEW. It's based on LabVIEW, but you can install the software on a computer and you can use it. For the motor system tool, it's not Excel based. It's an independent software. You can register, download, and use it. And also it has webinars, and also it has cases you can practice by own.
Okay, Mr. Wo, so we are coming to the end of the today's session, and
Yeah.
I request you to Dr. Khunam, maybe is willing to ask the question. Maybe we will allow you, sir, in the next day, so that you can ask the question with the next presenter.
I think you can, because in the next, no problem.
Yeah. So with this, thank you all the.
And we have one more engineer, Dr. Amber. That's
Yeah,
right.
Mr. Khunam is there. Hello. Okay, please, sir, you can ask any question.
Yeah, no problem. I'm free, so you can ask me more questions if you want.
You are on me. Please, you are muted. Dr. Khunam, you are muted, please. Please unmute yourself.
Okay, hello, can you hear me now?
Yeah, now it's okay.
Okay, hello, thank you so much for such a wonderful training session. And thanks to Hugo, I really learned a lot about the motors.
Yeah.
I was wondering, in Pakistan, most of the industries, there is a lot of dust. Inside the industry, there is a lot of dust.
Yeah.
So the motors are being.
We cannot hear you.
It is not, sometimes.
You mean the motor is dirty? The working condition is quite poor.
Yes, it's not easy to clean its surface. There is a lot of dust there. So I have visited a lot of industries, and I don't see any monitoring system for the motor's energy consumption. So I was wondering, should we install a three-phase meter on each motor?
No, I think maybe I'm going to introduce you something different because tomorrow or maybe on Thursday, this is a smart meter. It has not to be installed, to the motor. Actually, it has to be installed to the cabinet or even the, any electrical power point, any
So how
electrical. Yeah, you can use the electrical the after transformer in the switch cabinet, anything, anywhere else that you want. Normally, independent for the electrical cabinet, electrical room. In that room, you can install such kind of stuff. You don't have to install, to the motor. But for the ABB expert tomorrow will introduce one technology called ABB ability. They use this kind of sensor, touch the motor, and then it use called low power Bluetooth technology to communicate between the sensor and the gateway. Then they use gateway to upload the data. Different technology, different approach. But from my point of view, we don't have to to install the sensor to the motor.
So
But
I will
for the
request you
electricity
to
monitoring, this is enough.
yeah. I will request you
I cannot hear you.
Mr. Tuller on
Dr. Khurram,
so that
your
we
voice
can,
is broken, please. You are on and off, please. Dr.
okay, can
Khurram.
you hear me now?
Yeah,
Can
now
you hear
but
me?
it's yeah, now it's okay, but it's on and off time to time.
Okay, all right. Okay. I
Yeah.
I was asking that about this three-phase smart meter. Could you please share the specifications of this three-phase smart meter?
No, it's not only about smart meter itself. I think it's about the technology chain. That's why I
Okay.
think with communication protocol and also maybe the gateway, even some cloud service. I will introduce maybe on Thursday and also maybe tomorrow and also Friday to share my insight of this. The specification you can, I think it cannot connect to internet. It has to be combined with the gateway. It cannot be work independently.
All right.
Okay. Okay.
Okay. All right. Thank you. Thank you.
No problem. So
Okay.
we can keep contact for the search because if you see the agenda, so I will give the presentation tomorrow. I will show the smart pump demonstrator, which is one solution for us to monitor the pump systems remotely from cloud.
Okay.
And also
All right.
on Thursday and Friday, I will explain something behind the meter, some fundamental elements that for the digitalization of the motor and also maybe the optimization of the system. I think I will do this introduction later this week. We have 4 days training. And also maybe I also want to remind you to keep your eyes on ABB solution because the ABB ability is one pioneering company's solution. Right? Because I'm not from a commercial company, so I think ABB solution is also quite interesting and also might be, that might fit your demand, but I'm afraid that that's from the commercial company's side. Okay?
Okay.
They provide good solutions, but the problem might be the price, the cost.
Okay.
Thank you.
Okay. Thank you, Mr. Ovo and Dr. Khurram. I think we're running over the time, so we wrap up today. Tomorrow we'll start at 2 o'clock Pakistan Standard Time. Yeah, I can see now Rolf is there.
Hello, Rolf. Are you back?
Hello, Mr. Rolf. Hello, Mr. Rolf.
Hello, Rolf. What's the problem of the internet connection? I did the presentation for the rest of your slides,
Yeah.
so it's okay.
I think if we can, use Teams software or Zoom, because I had been experiencing a lot of trouble today. So it will be great.
We'll try it, sir, but this is our software, no? On the subscription. Maybe for the team, I need to talk to the authority. So
Sumo team might be better, but I
okay,
don't know.
I think for the role part already Mr. Hugo covered. So maybe Rod maybe take sometime tomorrow or the next day. So we'll wrap up today and we'll meet it again for tomorrow. So thank you everybody. Thank you. Thank you
All
all.
right. Thank you. Bye.
Thank you.
Okay, bye-bye. This class? Yes.